Welcome. We are discussing our third chapter, Calculus of Vector Fields. In the second module, we introduced the notion of vector derivative of a vector field and then studied its properties. In the coming module, that is the third module, we are going to introduce the notion of total derivative of a vector field. We shall also come to know what do we mean by differentiability of a vector field at a point of its domain. In this module, we shall study the notion of differentiability and total derivative of a vector field, say f, from A to Rm, where A is a subset of Rn. To initiate the notion, let us revisit very briefly the concepts of first, differentiability and total derivative of a scalar field G from Rn to R. We discussed this in chapter 2, module 5. Secondly, the differentiability of a vector field H from R to Rm. This thing we discussed in chapter 1, module 2. We recall that a linear transformation is a structure preserving map between two vector spaces. A map between two vector spaces over the same field is called a linear transformation, provided it is additive as well as homogeneous. An important thing about linear transformation is that one linear transformation can be completely determined by knowing its action on a basis. Now, we start our recalling the old notions. First one, let A be a subset of Rn. A is an interior point of the set A and G is a map from A to R. So, G is a scalar field defined on the set A. We say G is differentiable at the point A if and only if there exists a linear transformation T from Rn to R and a scalar function EAV such that for every suitable V we can express G of A plus V equal to GA plus TV plus norm V EAV, where EAV tends to 0 as V tends to the 0 vector. By suitable V, we mean that G of A plus V should be defined, that is A plus V must be in the domain of G, that is the set A. So, if we look at the expression, we can find we are approximating the change of G, that is G of A plus V minus GA. Let A be a subset of Rn, A is an interior point of the set A and G is a map from A to R, that is G is a scalar field defined on the set A. We say G is differentiable at the point A if and only if there exists a linear transformation T from Rn to R and a scalar function EAV such that for all suitable V we can express G of A plus V equal to GA plus TV plus norm V EAV, where EAV tends to 0 as V tends to theta. Here by suitable V we mean that G of A plus V has to be defined, that is A plus V has to be a member of the domain of G, that is in the set A. If we look at the expression, we can find basically we are comparing the increment of G, that is G of A plus V minus GA by the quantity TV plus norm V EAV. This linear transformation T from Rn to R is unique and is called the total derivative of G at the point A. We usually denote it by the symbol G dash A. Now, we consider the case which we studied in our first chapter. Let S be a subset of R, A is an interior point of the set S and H is a map from S to Rm, that is H is a curve in some neighborhood of the point A. Then H is differentiable at the point A if and only if there exists a linear transformation, say U, from R to Rm such that for all suitable T, that is A plus T in S, we can express H of A plus T equal to HA plus UT plus mod T EAT, where EAT tends to 0 vector as t tends to 0. Here also we are approximating the change in h, that is h of a plus t minus h a, by the term u t plus mod t e a t. So, now we are in a position to introduce the notion of differentiability and total derivative in case of a vector field. One can note that there is another way to treat a vector field, say f from Rn to Rm. It can be considered as composition of a scalar field h from Rn to R followed by a curve g from R to Rm. In the following part of this module, we shall use the symbols theta n and theta m to denote the 0 vectors of Rn and Rm respectively. We introduced the notion of differentiability and total derivative of a vector field. Let A be a subset of Rn, A is an interior point of the set A, and F is a map from A to Rm. That is, F is a vector field defined on the set A. We say that F is differentiable at the point A if and only if there exists a linear transformation T from Rn to Rm and a vector function EAV such that for all suitable V, that is A plus V belongs to A, we can express f of A plus V equal to Fa plus Tv plus norm V EAV, where EAV tends to the 0 vector of Rm, which we denote by theta m, as V approaches theta n, that is the 0 vector of Rn. Comparing, one can check that EAV will be 1 by norm V times f of A plus V minus Fa minus Tv, provided we assume V is non-zero, and we consider V such that norm V is very small. Equivalently, we can express that norm of EAV equal to 1 by norm V times norm of f of A plus V minus Fa minus Tv tends to 0 from the right, as V tends to theta n from the 0 vector of Rn. As V tends to 0 vector, V is never the 0 vector, so norm of V is never 0. That is why we can put norm V in the denominator. This linear transformation T from Rn to Rm is called a total derivative of f at the point A or a differential of f at the point A, and we use symbols f dash a or dfa to denote T. We note that the domain of T is Rn, although the domain of f may be a proper subset of Rn. Now, we show that the total derivative of a vector field at a point which is an interior point of its domain, if exists, is unique. That is, we are showing the uniqueness of total derivative. Let us assume, if possible, that there exist two linear transformations T1 and T2, both from Rn to Rm, satisfying the above condition. In such case, we can find two vector valued functions u1 and e2 such that for all suitable v we can express f of A plus V equal to Fa plus T1 V plus norm V E1 AV, and similarly f of A plus V equal to Fa plus T2 V plus norm V E2 AV, where E1 AV E2 AV tends to theta m as V tends to theta n. Then we have for V different from theta n, T1 V minus T2 V by norm V, this equals E2 AV minus E1 AV. We take the limit of both the sides as V approaches the 0 vector of Rn. So, we get limit V tending to theta n T1 V minus T2 V by norm V equal to limit of E2 AV minus E1 AV as V approaches theta n. Now, both the limits exist and equals theta m. So, we have theta m minus theta m, that is theta m. Now, in the above we put V equal to HU, where H is a scalar and U is a non-zero vector in Rn. Then we can easily check that H tends to 0 if and only if V approaches the 0 vector in Rn. Consequently, the limit T1V minus T2V by norm V as V approaches theta n equals limit H tending to 0 T1HU minus T2HU by, now norm V is norm of HU, by the property of norm this is mod H norm U. Now, we apply the homogeneity property of T1 and T2. So, T1HU we can write this as H T1U. So, we have limit H tending to 0 H by mod H T1U minus T2U by norm U. Now, the quantity T1U minus T2U by norm U is independent of limit, and the value of H by mod H is always plus minus 1 depending on whether H is positive or negative. So, we have the value of the limit as plus minus T1U minus T2U by norm U. Now, the value of limit was earlier calculated as the theta m. So, we find that T1U minus T2U by norm U equal to theta m. That is, for every U different from the 0 vector of Rn, T1U equal to T2U. Now, T1 and T2 are two linear transformations defined on the same domain. If we want to prove that they are same, we have to prove that for every vector in the domain they gives the same image. This was proved for every non-zero vector. Now, we know any linear transformation carries the 0 vector to the 0 vector. Therefore, we have T1 operating on theta n as well as T2 operating on theta m, both gives us the theta m, that is the 0 vector of Rm. Thus, it is proved that for every vector in Rn, the image of U under T1 and T2 are same, that is for every U in Rn, T1U equal to T2U. In other words, T1 equal to T2. This proves the uniqueness of the total derivative. So, now we can say this linear transformation T from Rn to Rm, we can name it the total derivative of f at the point A or the differential of f at the point A, and is usually denoted by the symbols f dash A or dfa. So, we write T equal to f dash A equal to dfa. One observation here, we mentioned it earlier, let us again recall it. First, we notice that the linear map f dash A has its domain Rn, although it may show happen that domain of f equal to A, which may be a proper subset of Rn. That is, the domain of the derivative map is more than maybe a superset of the domain of the given vector field. Next observation, the total derivative f dash A, if exists, is a linear transformation defined on Rn. For every V in Rn, f dash A operated on V is a vector in Rm. One remark, since A is an interior point of the set A, we can always find an open sphere SAR subset of A. So, we can always find V such that A plus V is in SAR, and this holds if and only if the distance between the vectors A plus V and A is less than R. That is, norm of A plus V minus A equals norm V less than R. Show that f of A plus V is well defined. In case the total derivative f dash A exists, we have f of A plus V equal to f A plus f dash A V plus norm V E A V, where E A V tends to the 0 vector of Rm as V tends to the 0 vector of Rn. The above equation is called the first order Taylor formula for f of A plus B. The term norm V EAV is a vector in Rm and is called the error term. Clearly, norm of EAV approaches 0 faster than norm V. Now we shall go through a result which gives us the relation between the total derivative and vector derivative of a vector field. The statement: let A be a subset of Rn, A is an interior point of the set A and F is a vector field defined on the set A whose codomain is Rm. We further assume that the vector field F is differentiable at the point A with total derivative T equal to F dash A. Then for all V in Rn, the vector derivative F dash AV exists and also Tv equal to F dash AV equal to the vector derivative F dash AV. If we know the components of F and V, we can write it in a more simplified form. Let F1, F2 up to Fm be the component functions. So, F1 to Fm are scalar fields defined on the set A and let V equal to V1 up to Vn. Then we have Tv equal to F dash A operated on V equal to summation from j equal to 1 to n inner product gradient Fj A and V Ej, and this equals to the ordered M tuple grad F1A V up to inner product grad Fma and V. Here E1, E2, Em denote the unit coordinate vectors in Rm. We start the proof. First we assume that V is the 0 vector of Rn. Since T from Rn to Rm is a linear transformation and a linear transformation carries the 0 vector to the 0 vector, we have Tv equal to T theta n equal to theta m. Now we check the other side. F dash AV vector derivative equals F dash A theta n. So, this is limit f of A plus h theta n minus Fa by h as h approaches 0. So, the numerator is nothing but f of A minus f of A, that is theta m. So, we have these as theta m. So, for V equal to theta n, we have Tv and the vector derivative f dash AV both are equal. Next, let V be any non-zero vector in Rn. Since f is differentiable at the point A, the first order Taylor formula gives f of A plus V equal to Fa plus Tv plus norm V EAV. For all V in Rn satisfying A plus V in A, that is, for all V satisfying norm V less than R for some suitable positive R. Here, V tends to theta n implies EAV tends to theta m. In the above relation, we put V equal to HU, where H is a real number, U is some non-zero vector in Rn. Clearly, H tends to 0 if and only if V tends to theta m. Then norm V equal to mod H norm U, and this must be less than R. Now, from the first order Taylor formula, we have f of A plus V minus Fa equal to Tv plus norm V EAV. Now, we replace V by HU. So, we have f of A plus HU minus Fa equal to THU plus mod H norm U EAHU. Now, T is linear. So, we can write this equals with H times Tu plus mod H norm U EAHU. Now, from the first order Taylor formula, we find f of A plus V minus Fa equals Tv plus norm V EAV. We replace V by HU. So, we have f of A plus HU minus Fa equals THU plus mod H norm U EAHU. We apply the linearity property of T. So, this equals with H times Tu plus mod H norm U EAHU. We divide both the sides by H. So, f of a plus hu minus f a by h equals with tu plus mod h by h norm mu E A hu. We consider limit of both the sides as h approaches 0. So, left hand side becomes limit of a plus hu minus f a by h as h approaches 0, which is nothing but f dash au, and the right hand goes to limit h tending to 0 tu plus mod h by h norm mu E A hu. The first quantity is independent of the limit. So, we have tu plus limit of that quantity mod h by h norm mu E A hu. So, this equals plus minus norm mu theta m. So, we have f dash au equal to tu. Writing v in place of u, we find that f dash av equal to tv, that is f dash a operated on v. So, first part of our result is proved. Now, from the relation between the vector derivatives of a vector field and its components, we find f dash av equal to summation j equal to 1 to m fj dash av ej. This equals with the ordered m tuple f1 dash av up to fm dash av, where e1 up to em are the unit coordinate vectors in Rm. Again, for each scalar field fj from A to R, where A runs from 1 to m, we have fj dash av equals summation L equal to 1 to n VL del fj del xl at the point A, and this equals with the inner product grad fj A and V. Therefore, we have Tv equal to f dash A operated on V equal to summation j equal to 1 to m inner product grad fj A V Ej, and that equals with the ordered m tuple whose first element is inner product grad f1 A and V, continued in this manner, the last term being inner product grad fm A and V. One remark here. From the above result, it is clear that for every V in Rn, f dash av is unique, and hence f dash a operated on V is also. So, we have another way to show that the linear transformation f dash a from Rn to Rm is unique. Actually, it depends on the choice of the scalar field f and the point A. Now, we shall go through another theorem which will give us the relation between the total derivative of a vector field and its partial derivatives. The theorem reads as follows. Let A be a subset of Rn, A is an interior point of the set A and F is a map from A to Rm. We further assume that the vector field F is differentiable at the point A with total derivative F equal to F dash A. Then for every vector V equal to V1 up to Vn in Rn, we have Tv, which is nothing but F dash A operated on V, equals summation I equal to 1 to n Vi dif at A equals summation I equal to 1 to n Vi del f del xi at A. We start the proof. We have already proved that for every vector V in Rn, Tv equal to f dash av equal to vector derivative f dash av. We consider the standard frame E1, E2 up to En of Rn, where Ei denotes the ith unit coordinate vector. Then f dash av equals f dash a operating on V1 E1 plus V2 E2 up to Vn En. Now, we know that f dash a is linear. So, this equals to V1 f dash a operated on U1 plus this continues, the last term being Vn f dash a operated on En. So, this equals V1 vector derivative f dash a U1 plus V2 vector derivative f dash a E2 summation up to Vn f dash a En. So, that is V1 del f del x1 at A plus V2 del f del x2 at A up to Vn del f del xn at A. In the extended form, the above expression looks like this: f dash a operated on V equal to V1 del f del x1 at A, which looks like the m vector del f1 del x1 A, del f2 del x1 A up to del xm del x1 A. So, plus V2 del f del x2 at A, that is in extended form the m tuple del f1 del x2a, del f2 del x2a up to del fm del x2a, and finally Vn del f1 del xna, del f2 del xna plus del fm del xna. From this we have, if f was a scalar valued mapping, then the value of n would be 1, and we can find f dash a v equal to inner product of the vectors del f del x1a up to del f del xna with v1 to vn. Now, we are going to show that continuity is a necessary condition for differentiability of a vector field. Theorem: for a vector field, differentiability at a point implies continuity at that point. Proof: let A be a subset of Rn, A is an interior point of the set A, and F is a vector field defined on the set A whose codomain is in Rm. We further assume that F is differentiable at the point A. So, our task is to prove that F is continuous at the point A. By the definition of differentiability, there exists a linear transformation T from Rn to Rm such that for every V in Rn satisfying A plus V in A, we can write f of A plus V equal to Fa plus Tv plus norm V EAV, where V tends to theta n implies EAV tends to theta m. As linear transformations are continuous at the origin, it follows that V tends to theta n implies Tv tends to theta n, which is nothing but theta m. Now, we take limit as V tends to theta n, then from both the sides of the first order Taylor formula, we have limit of V tending to theta n f of A plus V equals limit of Fa plus Tv plus norm V EAV as V tends to theta n. The first quantity is independent of limit. So, we have Fa plus limit V tending to theta n Tv, which eventually is theta m, plus limit norm V EAV V tending to theta n. So, the last term approaches theta m faster than V. So, we have limit of f of A plus V equals Fa as V approaches theta n. Hence, f is continuous at the point A. Now, we shall discuss a necessary and sufficient condition for differentiability. Theorem: let A be a subset of Rn, A is an interior point of the set A, and F is a vector field defined on A whose codomain is Rm. Then, F is differentiable at the point A if and only if there exists a linear transformation T from Rn to Rm such that limit V tending to theta n of the quantity norm f of A plus V minus Fa minus Tv by norm of V equals to 0. We give the proof. First, we assume that f is differentiable at the point A. By definition, there exists a linear transformation u from Rn to Rm such that for every suitable V in Rn, we can write f of A plus V minus Fa equals uv plus norm V EAV, where V tending to theta n implies EAV tends to theta m. From this, we have norm of f of A plus V minus Fa minus uv by norm V equal to norm of EAV. We take limit of both the sides at V approaches theta n. So, we find limit of V tending to theta n norm of A plus V minus Fa minus uv by norm V equal to limit of V tending to theta n norm EAV equal to theta m. So, this shows that u equal to t is the required linear transformation. Now, the other part. We assume that there exists a linear transformation T from Rn to Rm such that limit of v tending to theta n norm of f of a plus v minus f a minus t v by norm v equal to theta m. And we have to prove that f is differentiable at the point A. From the given condition corresponding to arbitrary epsilon positive, there exists a delta such that whenever norm v positive but less than delta, we have norm of f of a plus v minus f a minus t v less than norm v epsilon. So, define a vector valued function EAV equal to f of a plus v minus f a minus t v by norm v, and this is a vector in Rm. Clearly, norm of EAV is less than epsilon. Now, letting epsilon tending to 0, we find norm of EAV tends to 0 plus, that is EAV tends to theta m. So, we can express f of a plus v equal to f a plus t v plus norm v EAV, where t from Rn to Rm is a linear transformation and v tending to theta n implies EAV tends to theta m. So, we have our first order Taylor formula, hence f is differentiable at the point A. We show some examples how can we use the notion of total derivative to define differentiability. First one, let f be a constant vector field defined on a set A which is a subset of Rn, and for every x in A, fx equal to c which is a fixed vector in Rm. Let A be an interior point of the set A and we choose V such that A plus V is in A. Then f of A plus V minus f A, that is c minus c, that is theta m. Now, our task is to express this as T v plus norm v EAV, where T is the linear transformation and EAV tends to the 0 vector faster than V. So, we can define T from Rn to Rm by Tx equal to theta m for every x in Rn. Clearly, T is a linear transformation. Also, let EAV equal to theta m for each suitable V. With this, we can show that f is differentiable at the point A with f dash A equal to T equal to the 0 transformation from Rn to Rm. Next example, let f be a vector field defined on a set A is a subset of Rn, where f is the restriction of a linear transformation T to the set A. We select any point A which is an interior point of the set A and we choose V from Rn such that A plus V is in A. Then we can express f of A plus V minus f A. By linearity of f, it is f A plus f V minus f A, that is f V. Now, we have to write this in the form T v plus norm v EAV, where T should be a linear transformation. So, our guess is T should be f. So, we can write this as f of A plus V minus f A equal to T v plus norm v EAV, where T equal to that map whose restriction over A is f and EAV is identically the 0 vector. With this, we find that f is differentiable at the point A with f dash A equal to T. So, in this module, we introduced the concepts of total derivative and differentiability. We also studied the first order Taylor formula for a vector field. We proved that differentiability implies continuity for a vector field. With this, this module is concluded.